Just going with this formula, it can be shown that a flow rate of 844.8 cubic inches per minute, or roughly 3.66 gallons per minute at 2000 psi, represents roughly 4.3 horsepower of hydraulic power. If the pump was actually consuming 5.5 horsepower of mechanical power from the prime mover, this means the overall efficiency at this point would be roughly 77.6%. Now, overall efficiency ordinarily peaks out inside a given pressure range, and it is in this peak region those valuing efficiency should try to run the particular pump. Returning to much lighter subject material, 3 types of positive displacement pumps are commonly employed in hydraulic systems: gear pumps, vane pumps, and piston pumps. Pumps, regardless of their type, can be classified as fixed or variable displacement pumps. A fixed displacement pump, as the name implies, is incapable of varying displacement per revolution. A variable displacement pump, in contrast, uses movable internal components to selectively increase or decrease displacement per revolution as required. Gear pumps use a pair of meshing gears to provide pressurized flow to a hydraulic system. All gear pumps are fixed displacement pumps. Vane pumps can either be fixed or variable displacement pumps depending upon construction. A vane pump uses a rotor and extendable vanes that scrape the inside of a cam ring. A fixed displacement vane pump keeps the relationship between the rotor and cam ring constant, whereas a variable displacement vane pump varies the position of the cam ring or rotor to vary displacement per revolution. Piston pumps can either be fixed or variable displacement pumps depending upon construction. A piston pump uses an angled plate to move pistons inside a piston block. A fixed displacement piston pump keeps the angle constant, whereas a variable displacement piston pump varies the angle to vary displacement per revolution. Later lectures at the Big Bad Tech channel will discuss gear, vane, and piston pump specifics and examine their internal construction and principles of operation in greater detail. For now, we can just ignore these annoying details and simply treat pumps as mathematically perfect entities that produce flow, being the product of displacement and speed. A fixed displacement pump rotated at a fixed speed produces a fixed flow rate, obviously barring the pressure-induced details we discussed earlier. A pump with a fixed displacement of exactly 0.5 cubic inches per revolution, driven at exactly 1800 RPM, produces 900 cubic inches per minute, or roughly 3.9 gallons per minute. A variable displacement pump rotated at a fixed speed, in contrast, produces a variable flow rate depending upon the adjustable displacement value. Let's say a variable displacement pump is capable of varying displacement per revolution anywhere from 0 cubic inches per revolution up to a maximum of 1 cubic inches per revolution, being driven at 1800 RPM. This means the pump can produce anywhere from 0 up to 1,800 cubic inches per minute, or from 0 to roughly 7.8-ish gallons per minute. If this variable displacement pump, driven at a constant 1800 RPM, was to provide a comparable flow rate to our previous fixed displacement pump, we'd have to adjust the displacement to 0.5 cubic inches per revolution. The obvious advantage of a variable displacement pump is that flow rate can be varied given a fixed rotational speed. The not so obvious advantage is that a variable displacement pump can produce no flow. At first, a pump producing no flow might seem a dubious advantage since a pump's purpose in a hydraulic system is to produce flow, but consider our previous discussion on closed center valves. When a fixed displacement pump rotated at a fixed speed producing constant flow encounters a closed center valve, pressure rises to that of the main pressure relief valve, which dumps high pressure flow to the tank because the dumbass pump keeps pumping away despite there being no need for flow. Consider, however, a variable displacement pump rotated at a fixed speed driving this same circuit. When the valve is moved to the closed center position for an extended idle period, the displacement can be adjusted such that the pump produces no flow. Aha! In this scenario, the pressure relief valve would not be actuated and energy not build up, only to be spilled. When the directional control valve is shifted to extend or retract the cylinder, the displacement can be readjusted such that the pump produces flow. The principle means this is accomplished is by using a pressure-compensated variable displacement pump. Note the schematic symbol for a pressure-compensated variable displacement pump includes a vertical arrow. Pressure compensation is a means of adjusting flow rate as a function of pressure. In an ideal scenario, the pump produces the desired flow rate at any pressure below that of the compensator setting, sometimes called the firing pressure, and immediately destrokes to 0 gallons per minute above this setting. Ideally, the firing pressure is set just below that of the main pressure relief valve, on the order of 200 psi less, such that the main pressure relief valve is not regularly actuated and only serves as an emergency backup. This ideal scenario is obvious wishful thinking, and a real graph of flow as a function of pressure for a pressure-compensated variable displacement pump might show a little roll-off due to increased leakage and decreased prime mover speed at higher pressures, and a noticeable knee and tiny tail at regions near the firing pressure. I'll come back to discuss this in a moment. First, let's examine a hypothetical scenario making use of a pressure-compensated variable displacement pump. Let's say the pressure relief valve is set to 1,200 psi, and the firing pressure is set to 1,000 psi. At pressures less than 1,000 psi, the pressure-compensated variable displacement pump produces a nominal flow rate of, let's say, 3.9 gallons per minute. When the directional control valve is in the closed center position, pressure rises to that of the compensator, at which time the pressure-compensated variable displacement pump destrokes to 0 gallons per minute. Pressure upstream of the directional control valve is 1,000 psi, but static, and no additional flow is piling up behind it like an English soccer riot. Given pressure is below the setting of the main pressure relief valve, it remains closed. Pressurized oil is just sitting there, ready to be put to use. This is what is often referred to as a high-pressure standby mode. High pressure, no flow. When the directional control valve is shifted into a position requiring flow, pressure falls to that sufficient to generate force to extend or retract the cylinder. Let's say an input of 500 psi is sufficient to extend the loaded cylinder. In this case, the pressure-compensated variable displacement pump provides the full 3.9 gallons per minute. When the rod reaches the limits of extension, flow stops and pressure rises to that of the compensator, in this case 1,000 psi. The pressure-compensated variable displacement pump again destrokes to 0 gallons per minute, all without the necessity of actuating the main relief valve. The pump is now again in high-pressure standby mode. High pressure, no flow. Dig? In both scenarios, the closed center, and when the actuator reached the limits of travel, pressure rose to the firing pressure, and the pressure-compensated variable displacement pump simply destroked to 0 gallons per minute and stopped pumping when the circuit didn't need it. A pressure-compensated variable displacement pump can be used for applications necessitating an actuator extend with a given force and then maintain that force for a lengthy stall period. For example, a cylinder used to compress a mold. While the molded piece cures, the cylinder must maintain constant extension force, otherwise the final product would be damaged. Yes, in a perfect world, one could theoretically shift the directional control valve back to the closed center position and lock the actuator in place. But the real world must take into account both leakage across the piston seals and the limited sealing ability of the spool in the directional control valve. This is where the knee and tail regions of the pressure-compensated variable displacement pump comes into play. Notice at pressures close to the firing pressure, the pressure-compensated variable displacement pump still produces a tiny amount of flow. This flow is intended to take the place of any liquid lost due to leakage and maintain consistent pressure, all without the necessity of actuating the relief valve. This is equivalent to easing your car into a parking space after a long journey, rather than just slamming it in there at 60 miles per hour like some amped up meathead. I will admit I find pressure-compensated variable displacement pumps overly mechanically complicated, but I do have special affection for applications like this, as should you. The mechanical workings of pressure-compensated variable displacement pumps aren't unknowable by any means, but trust me, taking apart something like a motor drive is a significantly less dirty task. All I'm trying to say is that with more moving parts, more parts have more opportunities to break. Long story short, never trust a part that moves. That and your lab partner. Never trust them, even if they don't move. Another application befitting a pressure-compensated variable displacement pump is that of our earlier example of directional control valves and actuators in parallel with one another that must be actuated independently from one another. When both directional control valves are in the closed center position, pressure quickly rises to the compensator setting and the pressure compensated variable displacement pump de-strokes to 0 gallons per minute, thereby saving the pressure relief valve the responsibility of relieving pressure. Pressure is at the compensator setting and flow is static. The system is in high pressure standby mode. When one of the directional control valves shifts position to move an actuator, pressure returns to a load-induced phenomenon and pressure falls to that sufficient to move the load. The pressure compensated variable displacement pump adjusts displacement to provide flow. When the actuator stalls at the limits of travel, pressure rises to the compensator setting and the pressure compensated variable displacement pump de-strokes to 0 gallons per minute and the pressure relief valve is not forced to actuate. If leakage occurs while in this position, the pressure compensated variable displacement pump provides just enough flow to maintain pressure and replace the fluid lost to leakage. Again, the advantage of this scenario provided by the pressure compensated variable displacement pump is that closed center valves can be used without the necessity of regularly actuating the main pressure relief valve, all the while allowing each actuator to operate independently of one another. Moving on, a closely related pumping scheme known as load sensing can be used to keep not only pressure but flow rate constant inside a given range. Before we examine load sensing, let me quickly introduce a valve known as a shuttle or valve, since they are commonly employed in load sensing applications. As the name implies, a shuttle or valve executes the logical OR function. Either one port or the other is being selected, but not both. A shuttle valve has 3 ports, 2 of which can be considered inputs, A and B, and a center third port, the output, X. A shuttle valve looks like 2 check valve seats with one shared ball, and that's really how it functions. When pressure at A is higher than B, the ball is forced to B's seat and A goes to X. In contrast, when pressure at B is higher than A, the ball is forced to A's seat and B goes to X. Thus, the shuttle valve is selecting which input, A or B, is routed to X. When a shuttle valve is employed in a load sensing arrangement, its purpose is to select which actuator line, A or B, is being sensed by pilot line X. When the hydraulic motor is rolling in one direction, A is higher pressure than B, and A is routed to X. When the bidirectional hydraulic motor is rolling in the other direction, B is higher than A, and B is routed to X. The shuttle valve therefore always routes the pressurized line to the pilot X port, regardless of the direction of rotation of the hydraulic motor. A load sensing arrangement is one in which a pressure compensated variable displacement pump senses not only pressure at its outlet, but also pressure at an additional pilot location. Given 2 pressure values, the pressure compensated variable displacement pump with load sensing can therefore sense the pressure differential across a valve. In this case, the pressure differential is read across the directional control valve. Recall from the directional control valve lecture, available at the Big Bad Tech channel, that manufacturers include a pressure differential as a function of flow rate entry. If the pressure differential is known, flow rate can therefore be determined. Pressure compensated variable displacement pump with load sensing can therefore keep flow rate constant for a given range by maintaining a constant pressure drop across the directional control valve. Again, I am not a fan of mechanically complex configurations, and I ordinarily prefer electrical-based control systems. However, I give full props to this method because it accomplishes a pretty sophisticated means of both pressure and flow control using techniques akin to primitive man performing complex brain surgery with nothing more than sharpened stones, sticks, and torches. Before we bring this lecture to a close, let me briefly discuss the related phenomenon of cavitation, aeration, and pseudo cavitation. These all are undesirable events that lead to excessive wear of components, deterioration of hydraulic oil, and if recurring, can eventually damage or destroy a system. Cavitation is an event characterized by a liquid undergoing a rapid depressurization event and a subsequent rapid repressurization. When liquid is rapidly depressurized, it can enter the vapor phase. Think of water exhausted into the vacuum of space. It boils away since there is no pressure to hold it in the liquid phase. Additionally, When rapidly depressurized, any gas dissolved in the liquid can come out of solution and form bubbles. When the liquid in vapor phase is rapidly repressurized, the bubbles rapidly collapse, forming shock waves, noise, high temperatures, and high-pressure jets of fluid that can pit and abrade metal surfaces. Here's a picture of cavitation effects on a piston pump valve plate. If cavitation occurred for any length of time, these components would exhibit a notable loss in sealing ability between the dynamically moving surfaces. Cavitation can occur at the pump when the viscosity of the fluid is too high to allow suction, among other causes. For example, consider system at startup on an unusually cold morning. Oil in the reservoir is cold and as such exhibits an unusually high viscosity and resists being drawn into the pump during the active suction phase. The pump essentially sucks up nothing but vacuum, and when vaporized oil is repressurized during the compression and exhaust phase, implodes with damaging effect. Cavitating pumps vibrate excessively, run hot, and emit a high-pitched whine, every bit as annoying as a 6-year-old looking for a lost toy. Cavitation at the pump can occur when the oil is too viscous to flow, when the suction line is improperly sized, when the suction line is clogged, or when the pump is too distant from the top of the pooled oil in the reservoir. To solve cavitation issues, fix these problems first before you even touch the pump. Too often, technicians race to replace the pump only for these problems to reoccur. Cavitation is not exclusively a pump phenomenon, but can also occur inside valves and actuators. Consider a double-acting cylinder lifting a heavy load against gravity, or tipping or tilting an overrunning or negative load. When the cylinder lifts the load, pressurized fluid supports it. When the directional control valve is shifted into the cross-connect position, pressurized liquid no longer supports the lifted load, and the load and cylinder crash to the limits of travel, and perhaps beyond. Note as the piston rod end face rips away from the liquid still in the rod end. This is a rapid depressurization event, and the oil can enter the vapor phase. As pressurized flow entering the rod end catches up, oil in the vapor phase is rapidly repressurized and implodes. Not only did the lifted weight crash to the ground uncontrollably, a cavitation event occurred in the cylinder. If this is a recurring event, lasting damage may result. We'll examine flow control methods and counterbalance valves in later lectures that permit not only the controlled descent of a lifted object, but also prevent cavitation from occurring. Aeration is a related phenomenon with a different source, but the same effects. Aeration occurs if air enters the suction line. For example, aeration can occur if the reservoir level is too low, and rather than sucking up liquid, the pump sucks up a mixture of air and liquid. On the compression and exhaust phase, rapid pressurization implodes the entrained air, similarly damaging the pump. Additionally, aeration can occur if the suction line is improperly fitted or has a crack or hole. Aeration is different from cavitation in that cavitation creates a vapor phase from depressurized oil, whereas aeration just sucks up air, then crushes it. Pseudo cavitation is kind of the same thing, only it occurs after the pump. Consider a hydraulic system with a leak that happens to form a pocket of air inside the system. When pressurized flow enters this region, the entrapped air implodes, similarly damaging the system. Pseudo-cavitation differs from cavitation in that cavitation creates a vapor phase from depressurization, whereas pseudo-cavitation just sucks up air and then crushes it. Pseudo-cavitation differs from aeration in that aeration's source is air sucked in by the pump, and problems ordinarily manifest themselves around the pump, whereas pseudo-cavitation's source is air sucked in above stream of the pump, and problems manifest themselves elsewhere in the system. Sometimes you'll hear aeration and pseudo-cavitation used interchangeably, but there really is a difference despite the same damaging results. Systems encountering cavitation, aeration, and pseudo-cavitation problems will have a noticeable tendency to run louder and hotter, as well as exhibit actuators with sluggish or erratic movement patterns, given air or oil in its vapor form is mixed with what is intended to be a solely liquid power transfer medium. Again, before you even touch a pump exhibiting signs of aeration or an actuator exhibiting signs of pseudo-cavitation, fill the reservoir, fix the suction line, or fix the leak in the system to get rid of the source of the problems. Alright, that is that. Although I tried to keep this lecture pretty low tech, there's a lot of important content in here. and it might be worth your time to revisit it all if you're not completely on track. Since the pump really is the figurative beating heart of a hydraulic system, it's essential you understand how pumps work and what might be the cause if they don't. In conclusion, this lecture discussed fixed and variable displacement pumps used to drive hydraulic systems. We discussed factors that influence flow rate and the different means used to control flow rate. We discussed volumetric efficiency, pressure compensated pumps, and load sensing arrangements using shuttle valves. Additionally, we briefly discussed undesirable cavitation, aeration, and pseudo cavitation events. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.